Okay, now here's a good rule of thumb. Sampling with replacement, and by sampling we mean conducting a sample. In the case of the example where we had people in their favorite colors, the population was really the entire, all 28 of those people. That was the population from which we're drawing. And then if we select one person, we're taking a sample of one person from that group. Or if we select two people, we are conducting a sample of size 2 from that group. And so you could kind of think of it that way. And when we call the sample space, you can think of the sample space as the space from which we could collect a sample. Okay, so if we're doing a sampling with replacement, meaning we're selecting items from the population, and then we put them back so that they could be selected again. I draw the name out of the hat, I look at it, and then I put that name back in the hat so that person could be selected again. These selections are independent. And sampling without replacement, these selections will be dependent. Okay, selections without replacement means I select a person and I don't put that name back in the hat, so they couldn't be picked again. That reduces the size of the sample space left, reduces the number of successful outcomes I might have, and so on. Well, selections that are dependent make the multiplication rule here a little more challenging. Sometimes it can be very tedious. Let's look at a big example. Suppose there are 5,248 students at the University of Sunnydale, and 3,357 of those students are under 30 years old. Find the probability of selecting a group of 10 students who are all under 30. Suppose I'm assembling a student, trying to get a representative sample of these students, and I get 10 of them. What's the likelihood that all 10 of the students I select are under 30 years old? If we do this with replacement, then all the selections are independent. Right, selections are independent, meaning I select the first person, and whether they're under 30 or not, I put them back in the pool from which I can choose students, and I could possibly select that same person again. That means every single time after the first selection I put them back, there are still 5,248 students left to pick from for the second selection. And then I put that second person back, and there's still 5,248 students to select from for the third selection. So if we're doing this with replacement, then this probability, this is basically the probability that the first is under 30 and the second student is under 30 and so on, right? And so what we're going to do, we would do this with multiplication rule. We would say, well, probability that the first is under 30 times probability that the second is under 30 times the probability that the third is under 30 times ... times the probability that the 10th one is under 30. Oops, I'm out of space here, sorry. Scoot my screen over there. Okay. And each one of these is simply 3357 over 5248. Well, since I'm multiplying this same fraction times itself 10 times, that's the same thing as just doing it one time and taking that to the 10th power. Okay, so I can use my calculator for this, see what we get. We take 3357 divided by 5248, 3357 divided by 5248, and then we're going to raise that. So that's the probability that I just select one student, the probability that that one student is under 30. Raise this to the 10th power, 0.01147. 0.01147. 0.0115. It's pretty unlikely. Okay, it's pretty unlikely that that's going to happen. It's a low probability that I'm going to select 10 students and they will all be under 30. Now, what if I do this with replacement? I'm sorry, without replacement. Well, then what we're going to end up with is we have to do conditional probabilities. And so we essentially have to say, well, let's see, the first one, the probability that the first one is under 30, and then times the probability that the second is under 30, given that the first was under 30. And then I have to multiply it by the probability that the third is under 30, given or assuming that the first and the second. Well, that's just tedious. That's ridiculous to write it all out, because by the time we get the 10th one, we're going to say probably the 10th one's under 30, given that all previous 9 ones are. So it's cumbersome to write it, but then to calculate it, probably the first is 30. There's still the full population of 5248 to pick from, and there's still a full 3357 that are successfully under 30. But then the probability that the second is under 30, given that the first one was under 30, well, I've already selected the first one, so there's only 5,247 people left. And assuming the first one was actually under 30, there are no longer 3,357 students under 30. There's only 3,356 that are under 30. And then the next one, I have to keep going. The next one, after those first two, assuming the first two were successfully under 30, there's only 5,246 students left. Both of those students I picked, assuming they were under 30, means there's only 3,355 total left that are under 30, and so on. Well, this is certainly doable, but it's much more tedious to have to calculate than just taking this one number to the 10th power. So I'm not going to make you watch me type it on the calculator, but we'll skip ahead and see what we end up with. So the number I got here in my calculator for this one was 0.011411495, that thing. For comparison, the actual number I got when I took the 3357 over 5048 to the 10th power, when we calculated it with replacement, was this. Now let's compare those two numbers. Not a whole lot of difference, right? And so because of this, this sort of implies why we can use this rule here. There's a nice convenient little rule. Now this is referred to as the 5% guideline. And I put that number up there. For cumbersome calculations, if the sample size is no more than 5% of the population size, we can treat the selections as if they are independent. Well, in this last example, the selection sample size was 10. We were selecting a group of 10 students, and 10 is definitely less than 5% of 5,248. And so we are allowed, by the 5% guideline for cumbersome calculations, we're allowed to do this much simpler calculation than this much more complicated one. And we see that, well, sure, this seems fine because the result we got, the resulting probabilities were so similar as to be the same out to, several decimal places. So now this doesn't mean that we're going to get the same exact number. It just means that it'll be a little bit off, but it's an acceptable error. It's an acceptable difference given how much easier it makes the calculations. So that's very important. Okay, well, we have many applications of the multiplication rule because in statistics we very often do samples. We conduct samples, surveys, or whatever from a population, and we want to know, based on this sample, how likely is this? What does this mean about the whole population's values, and so on? And does this lead us to conclude that our assumptions are accurate or our assumptions are incorrect? Can we conclude that this medication is more effective or less effective, or has less side effects than this other currently used medication, and all sorts of things. And so we need to be able to figure out what the probability is of having this many values in a sample that actually have these symptoms or whatever. So suppose we are looking at births of children. Find the probability of having 17 consecutive male births, assuming the probability of a male birth is 1/2 each time. Now, with replacement, without replacement doesn't apply here. It's not like I'm putting the babies back after they've been born. So these are all independent. We assuming that each birth, it doesn't matter what the previous birth was. Whether the previous birth was male or female doesn't increase or decrease the likelihood that the next birth will be male. So let's see what we get here. This probability, this would be the probability that the first birth is male, and the second is male, and so on. So, as we said, all of these events are independent, so we don't need to worry about conditional, this one given that one, any of that stuff. We just simply multiply them all together. Probability that the first is male times the probability that the second one is male times, and so on. Well, those are all the same. Every one of those is 1/2. So we take 1/2 times 1/2 times 1/2, 17 times. That's 1/2 to the 17th power. And so we can quickly get that on our calculator as 1 divided by 2. And then we raise that to the 17th power. And we get this. 0.00007. There we go. Well, we might want it exactly. So actually what we could do if we wanted to, raising a fraction to the 17th power really means we're raising the top to the 17th power and the bottom to the 17th power. 1 to the 17th is just 1. And 2 to the 17th is 131,072. 131,072. So that's actually the exact probability. And of course we can verify. We take 1 divided by 131,072. We get that same decimal number we got before. Okay, so with the earlier example I did at the beginning of chapter 4, talking about the rare event rule, and from my personal experience, this happened in my my genetic line. There were 17 males born in a row. My dad, my uncle, his brothers and cousins, and my kids and nephews, males, 17 males in a row. And the probability of occurring randomly, if it really is 1/2 each time, is, I said, about 1 in 130,000. Well, that's the actual number for that. Now that we've seen the multiplication rule, we can calculate that. And so that allows us to conclude, in this case, that that assumption is probably wrong. The assumption in my personal situation that each birth has a 50-50 chance or 1 in 2 probability of being male, that assumption is probably wrong. Because if that was correct, it's really unlikely that this could have happened. It still could have happened by chance. It's certainly possible that this could have happened by chance, and it really is 50-50 each time. But the much more likely explanation is that, for whatever reason, my genetics are not producing as many of the male chromosomes than the female, or whatever it is. It's been a while since I took biology, sorry. So there you go. That is the multiplication rule.